So previously we had seen an example of proving a language is not regular using the pumping lemma. Now before we get into seeing some more examples, I thought it'd be a good idea we kind of revisit what we talked about so that you get a general game plan. So this is a common way of going about using the pumping lemma to prove a language isn't regular via contradiction. So recall this is the pumping lemma. So for any regular language L, there exists this constant called the pumping length, such that when I have this pumping length, and I must stress this depends on the language in question, depends on L. You can't just pick any P. It just exists, right? But it is the case that if you give me any string in the language such as length is at least the pumping length, there exists a way to dissect W into three parts, X, Y, and Z, such that it satisfies the following three properties. So it's really a question about it's about a sufficiently long string. So if the string is long enough, there's going to be a way to be able to decompose or dissect it into three parts such that the Y part, the middle part, isn't empty. But the first part of the first two parts, X and Y, it's going to be at least the pumping length. And it'll be that you can keep producing more and more strings that belong to the language. For any k greater than or equal to 0, x, y to the k, z, that means you could repeat the y part 0 or more times. So I got x, y to the k, z. This belongs to the language as well. So you might say, Dan, well, when we see in our example of proving a language isn't regular and we use the pumping lemma, we used contradiction. I thought it'd be a wise idea I go through just the general game plan I used in that proof. So if I were going about this using contradiction, what's the first thing I do in a contradiction proof like this? Well, I assume that the language is regular, right? So what I do is I assume L is regular, right? So if my goal is to show that L isn't regular, I'll just presume it is. And if it is, then it has to satisfy the pumping lemma, right? So that means that there's going to exist this pumping length P. So you're just given, you get this for free as a result of that assumption. So you're given P, but you don't know what P is, right? Somebody just gives it to you. I don't know who it is, but the point is that it exists, right? Now, here's the catch. Once you have this P, you know that for any string of a sufficient length, it satisfies all of this, right? So if our end goal is to come up with two strings. One string that I'm going to pick out of these ones, right? Because it has to satisfy this for all strings in the language, right? So I want to be able to pick a string such that W is in the language, but then I also want to show you that I could use this fact to come up with another string that should be in the language because of this property here, the third and last one there. I want to say that this is in the language, but I also want to show you that x, y to the k, z isn't in the language at the same time, giving me a contradiction. So I want to pick W such that I can take advantage of some properties here. The most common strategy is to try to get it so that I pick an appropriate K, such that because the pumping limit tells me this is in the language, I want to show you that that string also isn't in the language, yielding a contradiction. So let's walk through this carefully now. So if it is that I'm given this, and I don't know what P is, so whatever I'm doing in my argument, I can't just fix what P, I don't get a choice of what P is. P is just given to me, right? But however, it has to be that for all the strings, it has to be of a sufficient length, I get to pick W, right? But it has to satisfy this property over here, right? So I get to pick this if I'm trying to come up with a way to derive such a contradiction, right? Because it has to be satisfied for all strings. So I get control over how I pick W. That's actually what I did in the proof. Now, here's the thing. When I pick this, there exists a way to write right? It's such that it looks like this. So we'll talk more about how we pick W carefully. There's a lot of ways you could pick W depending on what the language is, presuming it is non-regular, right? But anyways, we're assuming that it is regular. But if it is the case that I pick this W, it has to satisfy, if it satisfies that property, meaning it's long enough, I should be able to decompose it like this, break it into the 3 parts. However, I don't know how it's broken into these 3 parts. So we're given, so you can imagine somebody somebody's saying, hey, look, that there's some way to do this, right? I don't know which way it is, right? I don't know. But if I'm careful about how I pick W, I'm able to actually tell you any way that somebody could have decomposed W. But here's the catch. If I'm able to pick W in a clever enough way such that my argument will work regardless of how somebody decomposes this, I should be able to take advantage of these properties over here, regardless of how it's decomposed. However, if I have to pick W in a somewhat more crafty way that requires me a little bit more work, I may have to use multiple cases. For example, it might be that the first or the second part may consist of different kinds of symbols, or maybe that the first 2 parts, say X and Y, consist of the same symbol. That's what happened in our first example. I'll talk more about that in a moment. But the point I'm getting at is that you want to argue in a way such that you're going to make sure that you aren't making any presumptions about how these 3 parts come about. That's the big thing I'm trying to get at. It's a very common mistake students make. Is they just assume that X, Y, and Z, like you know exactly what X, Y, and Z are. Often the mistake is that you get it backwards. Is that you're presuming that you know what this is because you presume that you fixed it. But the problem is it's actually that you're trying to form an argument that tells you what regardless of how you decompose it, what it will look like. If you don't know what it looks like, you're going to have to break it into cases. But for a lot of the examples you commonly see, there's often a very nice way you can, depending on how you pick W, you can argue regardless of how you decompose the string into the 3 parts, that you get these guys over here, right? And that's what you want. You don't want to make any assumptions about how this is done, unless you pick W in a special way that makes sure that X, Y, and Z have a particular form. And then you have to play with it a little bit more from there. Hope that's very clear. This is a common pitfall for students, is that they just sort of say, hey, look, Dan, hey, look, I know that it could do this. But the thing is, there exists some way to do it. I don't know what it is, just like I don't know what the pumping length actually is, right? I don't know what it is. The point is that if you pick W carefully enough, you should be able to make an easy argument about how X, Y, and Z are organized. So for example, you often will assign frequencies, how many symbols of a particular kind are in W, and then break it into cases. Another thing you might try doing is you might try to pick W in a special way such that you know exactly what's in a certain part of the decomposition or dissection of the string into these 3 substrings, such that you can yield a contradiction, which is often what you would like, so that you don't have to do a lot of work. Because if you could get away with a nice, elegant argument that is correct, that's much better than having to exhaust 3 to 6 cases at least. Maybe less, maybe more, I'm not quite sure. But the point I'm getting at is that you want to make an argument such that you can't make any assumptions about this. Unless you pick W in a very special way, can you point at this and say, yeah, the decomposition has this property, and I need to observe that property. Now, once you have that, once you pick W, you know that there's some way to write this. You don't know what it looks like. Remember, just think of it like it's in a box, right? I want to be able to say something about what's in the box. So I don't know what X, Y, and Z are. I just know if I pick W, that if I looked in this box, hypothetically speaking, I should be able to tell you that X and Y have a particular thing going on, but I don't know what X and Y actually look like. If I were to like pick, if somebody just gave me the way it was done. I hope that's clear. So if I pick W appropriately, and I have this way of decomposing it, then I get these properties. So these are things I know about how this dissection occurs. So the Y part's non-empty. That Y occurs in the first P symbols along with X. So it means it's going to be occurring some part at the beginning of the string. But you remember, I must stress that this is less than or equals. That means that there's other stuff that could happen with the Z part, right? Another thing, and like I said, the end game is to try to get over here, is that I would like to be able to pick so that X, Y to the KZ isn't in the language. So that's how I'm going to yield the contradiction, because the pumping lemma tells me that this is in the language, but I want to pick K. Remember, since it's for all, I get control of how I could pick K, because it should work for any K, right? So if I could do this, this is a very common strategy for using the pumping lemma to yield the contradiction. So hopefully that is clear to everybody. So I thought I would revisit this idea, and I really want to focus in on this part and how you pick the string W. So we're going to talk about that now. And I'm going to revisit an example that we did earlier, where we considered a language that looked like this. Where we had shown that if your string consists of equal numbers of zeros and ones, then we show that this actually isn't a regular language. And we use a strategy much like this to prove it. So I want to talk a little bit about the two things I really want to emphasize. The selection of this W and how this decomposition exactly works. Because remember, I don't know how the decomposition occurs, but I need to be able to consider all possibilities of when that how it might occur, right? So I want to talk first about the decomposing aspect, and then I'm going to talk about picking W. So let's talk about this. So decomposing X, Y, and Z. So I'm going to lay this in the context of this simple example that we did, just to help us see that sure, there's other ways that the string could be decomposed and how exactly the selection that we used worked. So in the proof, we had actually selected for string W, in this step, we had picked this one, 0 to the P, 1 to the P. So I want to really think about this carefully and see exactly what's going on here. So by how we selected W in the proof, we obtained a simple way, any split or dissection, any split of X, Y, and Z can happen for an arbitrary P greater or equal to 1. So remember, I don't know how this splitting occurs, the decomposing of string W works. So what I do is I pick W in a way such that I can say things about how the decomposition occurs. So how the split happens. So you'll notice, for example, here, and the reason why I picked this one was because if you look at the way the conditions of the pumping lemma work, x and y occur within the first p symbols, right? So it means that x and y happen somewhere in this first part where there's a bunch of zeros. And what we did was we picked our k value, and for the third condition, we picked it such that we obtained a string which had less zeros than ones, right? So you'll notice that when I picked this string, I did it such that I forced x and y into one part of the string, as opposed to allowing y to wiggle around or z to wiggle around. And I must stress that z can wiggle around, but the point I'm getting at is that I was able to say something about what happens with x and y, and namely what happens when I pump y. I didn't really care as much about what was going on with z, right, in this example. So let me break this out a little bit more carefully now, because I didn't really say a whole lot about z. That is, you can imagine I have 0 to the a, 0 to the b, I have 0 to the c, and 1 to the p. So this is what the string would look like, where, so like this will be, it could take any one of these here, where p is going to be equal to a plus b plus c, and the length of xy is equal to a plus b, which is at most the pumping length, and the length of y, of course, is strictly greater than 1. So when I pick this string w, any way that x, y, and z are dissected actually looks like this. Did you already see that? So the point I'm getting at is that when this split occurs, I don't know what a, b, and c are, namely because they have relationships with x, y, and z. All I know is that a plus b plus c has to equal p by how I pick the string w. So if you actually go back to the proof that we had seen, there's actually several different values for k. Remember that last step where we yield the contradiction? If you actually look at this carefully, you can actually see that different values of k actually work. Many different values for k work to yield a contradiction. Because remember, the y part here, the point is that it's the 0 to the b part, right? And if I take control of that, you'll notice that, remember, this altogether equals p. That's why I have equal numbers of zeros and ones, right? So what we did in the proof was we took advantage of the fact that this part right here, the y part, we knew that this y part has at least one symbol. So what we did was we played around with pumping that y part, right? So notice that if I use k is equal to 0, we get exactly what we had before. And this is actually what we had in our proof, was 0 to the a plus c, 1 to the p. And notice that a plus b is strictly less than p, right? And that tells you right away that there's less zeros than there are ones. And that's actually one way you could have explained how we yielded the contradiction. That's an alternative way of writing out what we did. So if you wanted to come up with a much more general way of writing out how x, y, and z's form might look like, it would look like something like this. And then we pump the y part. So in this case, I just did it 0 times. And this is the way we actually did it in the proof that we had seen for our example. So that works. Notice that I can't use 1, right? Because if I used 1, it would mean that I get this back, right? However, if I go k is equal to 2, that means I'm going to pump y. such that I get 0 to the a plus 2b plus c, 1 to the p. Where now, if you look at this carefully, you end up with a plus 2b. That's what we had over here for x, y, right? And then I'm going to pack on the c, which is the zeros component, the zeros related to z. Well, look at this. Well, now that is equal to p plus b. And because b is, in fact, positive, that means that this is strictly bigger than p. So that indeed works, right? So you could have went through the same proof and instead would have considered x. So in this case, you would consider x, y squared, z. That's what you would be doing here for k is equal to 2. So you can try more and more values. You can see quite quickly that, that many values. So I'll let you think about which values would work. So it's not very hard to see, but you know for sure k is equal to 1 you would never do for this. Specifically how we picked our string here. But remember, the big thing I'm getting at, remember, for any way W can be split, we need to show a contradiction occurs. Because I don't know how it's done. Because I just know that it's capable of doing this such that we had the 3 properties, right? But I don't know exactly what x, y, and z actually look like, right? Unless I pin down its form based on w, and then I can make observations based on how I pick w. But the thing is I can't just tell you that x, y, and z have, like they say, there's exactly this many, this many, this many. I don't have control over that. Notice that I'm using variables here to say, okay, well, this x part, okay, there's 0 to the a. So a has something to do with how x is appearing to me. B has something to do with how this splitting occurs, and of course C as well does as well, right? So remember, I don't have control over A, B, and C. However, in the third property, the one where I select K, I actually can control what happens with how many of a certain type of symbol, whatever's in the Y part, occur. So I want to pick W carefully such that I can easily control Y. So here's my other tip. So be careful when picking W. So in our example, over there, when we pick this W here, so we pick W, so at least P symbols consisted of 0. Of zeros. So the reason why we did that is that we didn't have to say anything specifically about how many of each there are. I could just simply say, okay, well, it means Y has only zeros, right? Because it occurs to that first P symbols, right? And that's how we played around with it. But if you want to really be careful about how you write it, you could also have written it out like I had over there on the right. So some choices for W work. And when I say work, I'm meaning to yield a contradiction in an easy to demonstrate way. Or just simply work at all. Others won't. So my big thing, and this is to come back over here, and as I said, try to select W so that the ways W can be divided into X, Y, and Z are easy to determine. Or as I would say, that you're trying to force it to have a particular form so that it's easy for you to say something about the X, Y part. Namely, so I could say something about Y. So that when I pick it, I could guarantee some property occurs. Are easy to determine. So I want to do a couple of examples just to give you some ideas for how you might go about this and how you could pick it. Because there's other ways you could have picked W, but be careful. So one thing I need to be very clear about is that in more complicated examples, you may pick W in a way such that you might need to exhaust more cases. Because like you've seen over here, when I wrote out those zeros and ones, I assigned variables that are associated with how X, Y, and Z are exactly split. How that split occurs. Now, here's the catch. If you pick W, depending on what example you're dealing with, it may be the case that that way those variables would be allocated, their values, depends on the split. And if it's a little bit more complicated, it might be that there exists more than one case for which the split might affect Y and your form of X, Y to the K, Z. So what I'm saying is, in our cases, it's going to be really nice, but often if you're dealing with a much more nasty example where finding that W, which in many cases you can find, but it might be the case you might need more cases because you might not be able to easily say, depending on what the X, Y, Z split does, depending on what that does, what it will look like. And then you need to be able to exhaust all of the ways that that string could look like depending on X, Y, and Z. Remember, you don't get to have a choice of what X, Y, and Z are. So you have to try all of them. So the whole trick here is that we pick W such that we force it to have a particular form so that I don't need a whole bunch of cases. But you might have to do that depending on how you pick W. So let's consider some examples. Let's consider if you picked we picked W, where it's 0 to the P over 2, 1 to the P over 2, with ceilings applied to both of these, meaning I'm always going to round up the result to the next integer if it's not an integer. So you might be looking at this and say, okay, Dan, first, is this W work? Is this one that's going to work well enough for us? Well, remember, the first thing that you need to make sure of is that the string W's length is at least the pumping length. So remember, I don't know what P is, but the thing is, it has to be at least P. Well, notice that if it was just P over 2 like this, well, P over 2 plus P over 2 is P, right? Well, remember, it could be the case that depending on what P is, that might end up being a fractional number, and that means that we can't have such a thing as a half symbol, okay? So we're rounding appropriately, but you'll notice that because of that, I'm able to guarantee that this is not going to be rounded down, and this is going to be something that will be one bigger if needed. But the point is that if you pick this, the string is going to be long enough. So it's going to have length that's going to be at least. So the length of this W is at least P, right? Because the ceiling of P over 2 plus the ceiling of P over 2 is at least P over 2 plus P over 2, which is equal to P, right? So yes, it has that property. But there's more of a catch with this way of picking W. Do you see it? There's a bit of a catch with this one. So we took advantage of the fact that all of y is sitting over where there's zeros, right? So we can easily make that determination by how we pick w. However, in the catch, if you tried this, and I encourage you to try it, you might need more than one case. That's where I'm getting at. Is y can consist of, and it could be the case that it could be all zeros. It could be the case that it's zeros and ones. Or 3, only ones. So now what you have to do is now you have to make sure that you check all 3 of these possibilities, right? So in your proof, instead of it having where we just make a simple observation about the form like we did, you would have it where you consider all possible or all 3 ways that the split could occur. And then you examine what happens. And then you go through the same strategy we did before. And because you considered all 3 of these possibilities for y, then it could be, then it has to be the case that you get the result that you're looking for, right? So this example, you shouldn't have issues with this example. However, you'll find very quickly that it's a little bit more work because now you have to look at these carefully. Let's consider another example. So you deal with a contradiction in each one of these cases. That's what actually you would do in this case. So it's like if we did our work but do it 3 times. Now, let's do another example. Let's suppose that you picked this. Something very similar. Suppose that we picked 0 to the p over 2 were the floor, and I have 1 to the p over 2 were the floor. Can I pick this for w? Can I pick this one? Is this going to give me any troubles? Any troubles at all? If I pick that as w? Well, let's go to our checklist. First, we need to make sure that the length it's long enough. Otherwise, we cannot use it. Well, let's take a look. Well, by the similar reasoning, right? We have p over 2, we have p over 2. And then, okay, so if it was p over 2, that's at least p. However, I'm rounding down these. Consider if, say for example, the pumping length just hypothetically was 1. That means it would be 1/2 rounded down, which is 0. And then you have 1/2 rounded down at 0. That's 0, right? It's not 1. Because that's what 1/2 plus 1/2 would be. So in this case, is not guaranteed that w is at least p. And what circumstance is it, though? When would we be able to just ignore the floor signs there, where we apply the floor? Well, it divides it by 2, so anytime it's even, right? Whenever except when p is even. If p was even, you're okay. However, like I said, you have no control over what p is. So I would not recommend you pick that for w. It won't be long enough. It's not going to cut it. So those are some tips I'm going to give you for proceeding with proofs for applying the pumping lemma to show a language is not regular. So remember the 2 big things. First, you have no control how the split occurs. The big tip that I'm going to give you is you pick w carefully so that you can make sure that the split, if it happens, it has a particular form that's easy to determine. So you want to think of it like you're forcing the string to have a particular form. However, remember, you don't know how x, y, and z are organized. You want to try to force w in a way so that X, Y, and Z have a particular property to them. So like in my example here where I pick 0 to the P, 1 to the P for this language and that proof, we did it so that I can force it so that X and Y always are zeros. Z might consist of some zeros and the rest of these ones, but the point is that Y is always going to consist of zeros. And that's what we took advantage of, and we explained carefully over here on this side. So please keep that in mind. The biggest mistake, biggest pitfall students fall into is they don't understand that you don't have control over X, Y, and Z. You don't get to pick them. Our argument has to yield a contradiction regardless of how the split occurs. But yeah, so those are some of my tips. Those are some of my tips.